Today we're going to talk about determinants of order n, the second part of a three-part series. First, let's review some of the properties of determinants of order n. Let's let A be an n by n matrix. We'll denote Aij tilde as that n-1 by n-1 matrix obtained from A by deleting row I in column J. Here are a few examples. When n is equal to 2, we can see that we can cross out the rows and the columns to find these smaller matrices Aij tilde. When n is equal to 3, we can do the same process, but you'll notice now that the smaller matrices are these 2 by 2 matrices. In this case, according to each entry Aij, we have a 2 by 2 matrix Aij tilde. Let's make a definition here. We'll define the determinant of an n by n matrix A recursively as follows. If n is equal to 1, that is, our matrix only has one entry, then we'll define the determinant as that entry, A11. On the other hand, if n is greater than or equal to 2, then we'll define the determinant by summing over the first row. Here we have a sum where we have a plus or minus, namely minus 1 to the 1 plus j, times A1j, this is the entry in row 1, column j, times the determinant of A1j tilde. Here we take the matrix A, cross out row 1 in column j. The sum of all of this is what we're defining as the determinant of A. That n by n matrix, where the ij entry is given as you see on the screen, is called the cofactor of A. Here the entry, the ij entry, corresponds to a checkerboard pattern, this minus 1 to the I plus j, times the determinant of Aij tilde. The transpose of this matrix is what we call the classical adjoint. We'll give a few examples. Let's say that n is equal to 2. We can cross out the first row and the first column, and then consider where we have A11 and A12. In this case, using the definitions on the previous slides, we see that the determinant of A is A11 times A22 minus A12 times A21. The cofactor of this matrix is given as follows, where you'll notice that the signs satisfy this checkerboard pattern. The transpose of this matrix, what we're calling the classical adjoint, gives us a formula for the inverse of a matrix A. In other words, the inverse of a 2 by 2 matrix is 1 over the determinant times the classical adjoint. As another example, let's consider n is equal to 3. Here, just like before, we can cross out the entries in the first row. From the diagram here, we can actually see that the determinant can be expressed using 6 terms. The cofactor matrix can be found via this checkerboard pattern, plus minus plus minus plus, times various 2 by 2 determinants. The classical adjoint is just the transpose of this matrix, and just like with the 2 by 2 matrices, the inverse of our matrix A is 1 over the determinant times the classical adjoint. For today's lesson, we'd like to go over what's called linearity in the rows. To do this, let's first recall some definitions. Let's say that we have two vector spaces V and W. Well, for a given well-defined map T from V to W, the following statements are equivalent. That is, for all x and y, T preserves vector addition, and for scalar C, T preserves scalar multiplication. This is equivalent to saying that T preserves linear combinations. A map satisfying either of these equivalent conditions is said to be a linear transformation. So here's the main result for today. Say that we have an n by n matrix A, and let's denote A1, A2 through A sub n as the various rows of this matrix. For any integer r between 1 and n, let's define t sub r as the following function. We'll start with a vector x from Fn, and we'll return a scalar determinant of b, where B is that n by n matrix obtained from A by replacing row R, namely the vector AR, with our given variable x. The claim is that this T sub R is a linear transformation. In the parlance, we'll say that the determinant of an n by n matrix is a linear function of each row when the remaining rows are held fixed. Before we continue, let's give an example of this to explain a little bit more what's happening. Let's take a look at the case when n is equal to 3, so that we have now a 3 by 3 determinant. In the case where R is equal to 2, we'll have the following matrix B. Here we've replaced the second row of B with the vector xyz. We're going to think of xyz as 3 variables. Upon computing the determinant here, we then have our desired function T sub R, which is a function of the variables x, y, and z. Here, we're simply taking the expression for the determinant as above, and we're replacing a sub 2,1 with x, a sub 2,2 with y, and a sub 2,3 with z. You'll see here from the expression for the determinant of b, we can combine the various terms together to see we have a coefficient in front of x, a coefficient in front of y, and a coefficient in front of z. We find these coefficients by realizing we have these two terms involving x, so we simply factor out the x and collect the terms. Similarly, we have two terms here involving y. We simply factor out the y and collect the terms. And finally, we have these remaining two terms involving z. Again, we'd simply collect the terms and factor out the z. This function that we have is actually a linear transformation. Let's go over the proof of this. First, we want to consider the following proposition as a function of the integer n. Remember that n here is the size of the n by n matrix. It goes as follows. Let's consider the proposition that says, let a sub 1 through a sub n denote the rows of an n by n matrix A. For each integer r between 1 and n, we'll define the function T sub r as the determinant of capital B, where B is that matrix obtained from A by replacing row R with the variable x. Remember that x is a vector. The claim is there exists coefficients C1, C2 through C sub n such that TR of x can be written in the form that you see here. Since we want to prove this by induction, let's first establish the base case. When n is equal to 1, then our 1 by 1 matrix A is just a scalar. In this case, R will simply be equal to 1, and our matrix beta is just the variable x. So its determinant is just the variable. So there's really nothing to do here because this function T sub 1 of x is just the variable x. In this case, because n is equal to 1, x really is a variable, not a vector. Now let's assume the inductive hypothesis. That is, let's assume that the proposition P of n0 is true for some positive integer n0. We're going to perform the inductive step. That is, we want to consider the proposition P of n0 plus 1. Let's now say that a1, a2 through a sub n0 plus 1 are the rows of an n0 plus 1 by n0 plus 1 matrix A. Recall that for every integer r between 1 and n0 plus 1, we want to define this function T sub r, which is simply the determinant of the matrix B that we obtain from A by replacing row r with our vector x. For the rest of this proof, we're going to consider two cases. For the first case, let's say that r equals 1. That is, we're going to replace the first row of our matrix A with our vector x. Now, when we try to compute T sub r of x, we're just computing the determinant of this matrix B, but again, our matrix B is defined so that the first row of B is just the vector x, and all of the other rows are just the rows of A. So according to the definition of the determinant, B sub 1j is just the variable x sub j, and bij tilde is just the matrix aij tilde. Again, once we cross out the first row, the rest of the rows of B look just like the rows of A. So combining all of this together, we do see that our T sub r of x is in the claimed form, where the coefficients C sub j can be found in terms of the matrix capital A. Now let's consider the other cases where R is between 2 and n0 plus 1. Recall that BIK tilde is that n0 by n0 matrix formed from deleting the first row and the kth column of B. In fact, we can really see what the rows of B1K tilde are. All of the rows would look like the rows of A, but we have to be a little bit careful here. Row R, if it were, is actually this vector x tilde, where we have to be careful that we actually delete the variable x sub k, because remember that we've deleted the kth column of our matrix capital B. The inductive hypothesis says that if we take a look at the determinant of B1K tilde, that we can actually express this as a sum in terms of the variables x sub j, where of course x sub k is missing. But if we just simply denote the scalar b sub kk to be 0, then we have a nice clean expression here, which is just a sum in terms of scalars times the variables x sub j. We can put this back into our definition for TR of x. Remember, this is the determinant of B, but according to the definition of the determinant, we have an expansion here along the first row. Our B1k, that scalar, is simply A1k, because remember that we didn't change the first row of B. We changed row R, where R is greater than or equal to 2. So B1k is just A1k. However, we just found an expression using the inductive hypothesis for B1k tilde, which means that we can express this determinant now as a sum involving the variables x sub j. So combining things in a different way, we again see that T sub r of x is a sum in terms of coefficients times the variables x sub k, which does show the proposition P of n0 plus 1 is also true. We're not quite done yet. We still have to prove that each of these transformations T sub r is really a linear transformation. That means we have to show that each T sub r is closed under, preserves vector addition, and preserves scalar multiplication. To this end, let's say that we have two vectors x and y. Then, just by playing around with the coefficients a little bit, we easily see that TR of x plus y is TR of x plus TR of y, so that TR does indeed preserve vector addition. Similarly, given any scalar c, then we see that TR of c times x is c times TR of x. So our transformation TR preserves scalar multiplication also. This does complete the proof of the proposition. Thanks for watching.